Okay, let's unpack this. We're going to drill down into some of the real unsung heroes of modern buildings,
Hmm.
the parts that let architects create these amazing looks. Without compromising on strength,
Right.
we're talking about aluminum architectural and construction profiles. They really define how efficient and, frankly, how elegant modern structures can be.
They absolutely do. I mean, these profiles are genuinely transformative. You see them everywhere, whether it's a, huge new commercial tower or maybe a really sleek home renovation.
Yeah.
They're the bits that connect the science of materials with that kind of high-end design vision.
And looking at the materials you shared with us, there's definitely one star here, aluminum. It seems to be the go-to now for architects, engineers, builders.
Oh, for sure.
And it's because of qualities nothing else quite matches, right?
Yeah.
Like this incredible strength to weight ratio. It resists corrosion really well. It's super flexible for design.
And the big recyclability.
Exactly. Hugely
Yeah.
recyclable. That sustainability angle is massive.
It really is. It's sort of the perfect foundation for what construction needs today.
Yeah.
So our mission for this deep dive is really to explore how these precisely engineered profiles work.
Right.
They come in all sorts of shapes, your standard T-sections, U-channels, angles, but also really complex custom extrusions.
Uh-huh.
And we want to see how they provide these like shortcuts to building faster, more sustainably, and giving you, the designer, the builder, the owner, more creative freedom.
Okay, so let's start right at the beginning. If I'm looking at plans, what is an architectural profile, like beyond just a piece of metal?
Sure. So you can think of an architectural profile as a structural or sometimes just a design-focused aluminum part. It's made using extrusion.
Okay.
And its job is, well, it can be several things. It might support something, connect different elements, or maybe just enhance the look or function of part of the building.
So like the bones and skin you said.
Yeah, kind of like the high-precision bones and skin.
Yeah.
And they're used all over the place: glazing systems, facades, window frames, even things like supports for false ceilings or the framing inside modular furniture.
That brings up the manufacturers. Our sources kept calling the big aluminum extrusion companies innovation partners. Now, that sounds a bit like corporate speak.
Huh. Yeah, it can sound like that.
But what does that actually mean in practice for the final product?
It means they're really involved in the engineering side of things. Yes, they have the big state-of-the-art extrusion presses,
Right.
but crucially, they use advanced tools like finite element analysis, FEA.
Okay, so simulation.
Exactly. They can simulate how a profile will behave under real-world stress before it's even made.
Ah.
This lets them tweak the design, maximize strength, but also, remove material where it's not needed. So you get these highly precise parts made consistently at scale, and they meet all the tough global quality and safety standards.
All right.
They basically solve the tricky structural problems digitally so you don't face them on the building site.
That makes a lot of sense. Optimizing material use saves weight, saves cost. But what about the competition? Why aluminum over, say, steel? Or composites? What are the trade-offs there?
Well, you're always balancing things with materials. Steel is, incredibly strong, great load-bearing capacity, high tensile strength. It's still essential for the really heavy structural stuff, main columns, big trusses.
Right, the primary structure.
Exactly. But the price you pay for that strength is weight. Steel is heavy. And it doesn't resist corrosion well unless you treat it heavily and keep maintaining it.
So if you're building something like a huge glass curtain wall, maybe 30 stories high, or putting in partition systems inside.
The weight of steel would just add enormous unnecessary load onto the building's main structure.
Okay.
Aluminum's fantastic strength-to-weight ratio lets engineers design lighter structures overall. That often means smaller foundations, sometimes even cheaper seismic bracing strategies. Plus, aluminum's natural corrosion resistance is perfect for anything exposed to the weather, like facades or railings. Much less maintenance over the building's life.
And what about composites? Things like UPVC or FRP fiber reinforced polymer, they seem to pop up.
But they do have their niches, yeah. Usually where things like thermal resistance or electrical insulation are the absolute top priority,
Ah, okay.
but they're often less customizable. If you need a really unique, complex shape for some architectural feature, aluminum extrusion is just incredibly flexible and scalable.
Right.
And critically, composites just can't match aluminum's recyclability. It's close to 100% recyclable without losing quality. For any project aiming for green building certifications, aluminum is a huge plus for hitting those zero waste goals.
Okay, this is where it gets really interesting for me. Let's move from the material itself to how it's actually used.
Yeah.
Let's talk specific profile types and how they change how buildings work.
Hmm.
I want to start with glazing and facade systems, because that's often the first thing you notice, the architectural signature.
Absolutely. And these systems are where engineering really meets aesthetics. The profiles used in glazing and facades aren't just about looks, they're critical for the building's energy efficiency and its structural performance, too.
How so?
Well, aluminum profiles let designers create these incredibly thin frames that can still hold huge, heavy glass panels for things like curtain walls. They provide the strength without being bulky.
I keep hearing about thermally broken profiles. Can you break that down for us?
Mhm.
Why is that so important for energy saving?
Yeah, that's a key concept. Aluminum itself is a really good conductor of heat.
Right, conducts heat and cold easily.
Exactly. So if you just had a solid aluminum frame going from the inside to the outside of a building, it acts like a highway for heat, pulling it out in winter, letting it pour in during summer.
A thermal bridge.
Precisely. A thermally broken profile cleverly inserts a layer of material with very low conductivity, usually a type of polyamide strip, right into the profile. The strip physically separates the inner aluminum part from the outer aluminum part.
So you literally break the bridge.
You stop that easy energy transfer. This separation gives you much, much better thermal insulation. It cuts down heating and cooling costs dramatically and helps buildings meet tough energy codes.
That's essential for those big glass facades we see everywhere.
Totally. You get the sleek look, the transparency, but without sacrificing insulation performance.
Excellent. Okay, now what about the standard sections? The workhorses, you mentioned angles, channels, T-sections, Z-profiles. What makes them different in terms of function?
These are like your fundamental building blocks, but yeah, each shape is good for specific jobs based on how it handles loads or makes assembly easier.
Okay.
So a T-section, for instance, is great for joining two things at a right angle or acting as a slim reinforcing rib. A channel or U-section gives you stability, good against sideways forces, so you see it in framing or maybe tracks for sliding doors.
And the Z-profile. That one seems a bit less common.
The Z-profile is quite clever for creating offsets. Think about cladding systems or roofing supports where you need to step the surface out or create a specific gap from the main structure. Ah, I see.
And the key thing with all these standard sections is they're manufactured to really tight dimensional tolerances.
Meaning they fit together perfectly.
Exactly. They just snap or screw together consistently, which cuts down on fiddly work and waste on site. Ideal for things like internal partitions, modular frames, that sort of thing.
We've covered the permanent structure, but what about during construction? Aluminum scaffolding and formwork? Seems like the lightweight aspect would be huge there for safety and speed.
Oh, absolutely. It's all about making the project run faster and managing the site better. Aluminum scaffolding is so much lighter than steel.
Easier to handle.
Way easier. Faster to put up, faster to take down, needs fewer people, and it's safer because the parts aren't as cumbersome. Plus, being corrosion resistant, it holds up well on rough outdoor sites.
Right.
And here's a big sustainability link. Aluminum formwork, the molds for pouring concrete, can be reused hundreds, sometimes thousands of times across different projects. That massively reduces the waste you get from traditional timber formwork, which is often single use. That reusability is a great point. And I guess that idea carries through to the inside too, with things like corporate office furniture profiles.
Precisely. It's the same logic. High strength, lightweight, modular framing. You see these profiles forming the backbone of modern office workstations, screen partitions, modular seating arrangements.
Allows for flexibility.
Huge flexibility. You can reconfigure office layouts relatively easily. The profiles provide the necessary strength and stability, but also contribute to that clean, minimal, professional look that's popular now. And they integrate really well with other materials like glass, wood, or composite panels.
So let's zoom out again and connect this to the bigger picture. How do these profiles perform across different types of construction? Thinking about strength, looks, sustainability in each area.
Okay, let's break it down. Start with residential projects. Here, homeowners value durability and low maintenance.
Yeah.
So aluminum is perfect for window frames and door systems. It doesn't warp or rot like wood, resists corrosion, so very little upkeep. Aesthetically, you can get much slimmer frames than with, say, UPVC, which means more glass, more light.
And the thermal break helps with energy bills.
Directly impacts the homeowner's energy bills, yes. And for things like balconies and railings, powder-coated or anodized aluminum gives a really polished look that lasts for ages.
Okay, now shift to commercial and industrial buildings. The demands there must be tougher.
They are. Performance under more demanding conditions is key. Commercial architects rely on aluminum for those big curtain wall systems we talked about. They need to handle significant wind loads and provide excellent insulation over huge areas. Inside, you see aluminum profiles used extensively in suspended or false ceilings and for mounting lighting grids. They offer flexible, strong support for all the building services, HVAC ducts, wiring, sprinklers. And because it's lightweight, it reduces the overall load on the main structure, which is really important in tall buildings.
Makes sense. And finally, big infrastructure and public projects. Bridges, stations, public buildings, things meant to last decades. Resilience must be paramount.
Absolutely non-negotiable there. This is where aluminum profiles really demonstrate their long-term value proposition. You'll see heavy-duty aluminum extrusions used for things like bridge railings and safety barriers.
Why aluminum there? Strength.
It's that combination again. Light enough for easier installation on potentially difficult sites, but engineered to be strong enough to meet very strict safety regulations and absorb impacts.
Okay.
For external facades and cladding on large public buildings, aluminum offers fantastic durability against weather, sun, rain, wind, pollution. It ensures the building keeps its integrity and appearance for much longer compared to materials that might degrade or need constant repainting.
Right. So let's bring this right back to the listener. If you're the person specifying, procuring, or maybe reviewing the designs for a project, choosing the right profile is obviously crucial. What are the key things you absolutely need to consider?
Yeah, you can't just pick a shape from a catalog and hope for the best. Step one is really fundamental engineering. You have to understand the load and structural demands.
What does that mean in practice?
It means doing the calculations. How much weight does this profile need to support? What kind of forces will it experience? For high-load areas like facades or main support elements, you need robust profiles, maybe I-beams, strong T-sections, specific channels, and you need to work with the manufacturer to make sure the specific aluminum alloy they use has the right properties for that load without making it heavier than necessary.
Okay, load is number one. What's next? Thinking long-term performance.
Environmental exposure. This is absolutely critical for durability. It's not just about day one, it's about year 20, year 50.
Right.
You need to consider, is this going near the coast with salt spray? Is it in a desert with intense UV and heat? Is it somewhere with heavy rainfall or industrial pollutants?
So the finish matters hugely.
Hugely. The profile needs a finish that can withstand those specific conditions. That often means specifying high-quality anodizing.
Can you remind us what anodizing is?
Sure. It's an electrochemical process that basically thickens the natural protective oxide layer on the aluminum surface. It makes it incredibly hard, wear-resistant, and super resistant to corrosion. Or if you need color, you'd specify powder coating, but making sure it meets industry standards, like AAMA certifications, which guarantee performance.
Got it. And we've touched on sustainability throughout. If I'm a project manager, what should I be asking my supplier about the green aspects?
Two main things. First, ask for evidence of the recycled content in the aluminum.
Because aluminum is highly recyclable.
Infinitely, without losing quality. Using high recycled content drastically cuts the embodied carbon, the energy used to make it. Second, insist on compliance with standards like RoHS.
RoHS, restriction of hazardous substances. Why is that relevant for a metal profile?
It ensures the specific alloy they're using is free from lead and other harmful heavy metals. This is essential for getting modern green building certifications like lead or BREEAM, and it also means a healthier building for occupants and construction workers. It's not just nice to have anymore, it's often required.
Makes sense. And finally, especially with those complex custom extrusions, it sounds like you can't just treat the supplier like someone selling nuts and bolts.
Absolutely not. That leads to the final and maybe the most crucial point. Consult with experts. Get the manufacturer involved early.
As an innovation partner.
Exactly. The good ones offer design support, they can help with prototyping, they have engineers who understand extrusion capabilities and limitations. Working collaboratively ensures your architectural vision can actually be built effectively, meeting the budget, the performance specs, and all the regulations.
Yeah.
And practically speaking, understanding their lead times for creating custom dies is vital for your project schedule.
Okay, so just to wrap up the core benefits here. Aluminum architectural profiles bring this powerful package. Lightweight but strong, naturally resist corrosion. They're relatively easy to fabricate and install, which cuts down site labor.
Big time.
Hugely recyclable, which
Yeah.
is critical now, and they let architects create these really sleek, modern looks that just weren't possible before.
Yeah, and what's really fascinating now, I think, is how this precision engineering, especially with custom extrusions, is shifting our expectations for how long structures, particularly public infrastructure, should last and perform. The source material points to aluminum profiles as being key to truly future-ready construction. And that brings up a really interesting question for the future. If we can now custom design these highly precise, corrosion-resistant, and reusable aluminum profiles so easily, lowering the barrier to complex, maybe even modular designs, how might that engineering freedom push architects and engineers to innovate materials and assembly methods specifically for end of life? Designing not just for longevity, but for perfect circular deconstruction, ensuring the next generation of buildings and infrastructure can be taken apart and reused just as easily as they were put together.